Hello everyone, and welcome to this webinar about building a modern data architecture on AWS. My name is Russell Nash. I'm a solutions architect with AWS, and I spend my time talking about all things big data and analytics. So I'm excited to spend the next little while with you talking about the modern data architecture. Now, just a quick logistics point. If you do have any questions as we go through the webinar, please use the chat window and post your question in there. Now, I won't have time to answer those questions in this hour, but what we'll do is we'll compile all of the questions and the answers, and then provide that that question and answer sheet back to all of you next week, also with access to the recording as well. So what I want to do today is take you through the modern data architecture as we see it, and firstly talk about some of the aspects that you want to see in your data architecture, and then look at 4 of the most common patterns and use cases that we see our customers building, and talk through those in a little bit of detail and kind of map them to this architecture, and you can see how it all hangs together. So firstly, let's look at some of the facets that you want in your data architecture. So the first one is scalability. So one of the things that comes up a lot in my discussions with customers is that they are running out of room in their database, for example, or they're running out of the ability to support more users, or they're not getting the performance out of it that they need. And so they're really looking for scalability at different points in the architecture as well. So that ability to be able to scale the components independently of one another is an absolutely key aspect of the modern data architecture, and we'll look at that as we go through. The second is flexibility. So one of the key things that's going on in the big data and analytics space at the moment is just constant innovation. So there's constantly new ways of doing things being made available, tweaks and changes to existing open source services, for example, and products. And so you don't want to get locked into a particular way of doing things. You want to be able to take advantage of these fantastic innovation that's going on in the industry at the moment. So that flexibility is absolutely key as well. The third thing is that it needs to be manageable. So one of the things that we'll talk a lot about as we go through this session is how do you manage a lot of these components? And you'll notice that when I start talking about some of the AWS services, we talk a lot about undifferentiated heavy lifting. And this is really work that you have to do in order to have the environment up and running, but it doesn't really differentiate you in whatever market you're in. It doesn't really allow you to differentiate against your competition. So that's the piece that we'd like to take off your plate and move it onto ours, so that we will do that heavy lifting for you, which allows you to focus on things that are going to have a much bigger impact on your organization or your business. The fourth aspect that's really important is that it needs to be cost effective. So one of the things, again, that you'll see we talk about is that you really want to make sure that the costs that you're incurring for your data architecture map very closely to your usage of that architecture. And so we're very much in favor of a pay-as-you-go type of model, where you simply pay for the storage and the compute and the services that you use, as opposed to having to pay upfront for something that you'll then grow into that might take you 2 years or 3 years to actually fully use. We think that it's a much better option to be able to pay as you go, and that leaves you with a much more cost-effective architecture. So we'll talk about a bit about that as we go through as well. So what we're going to do is we're going to look at this architecture through a bit of a framework, and that framework's going to start with the sources of data that you have, and then what are the options for ingesting those into your environment. And then we're going to look at 2 separate layers. So the first is called the scale layer, or often called the batch layer. And this is where you'll do a lot of the batch processing that you need to do. So as files come in, maybe they come in once a day, or maybe they come in once an hour, but it's characterized by doing things in a kind of batch type way. So we'll talk through the best way to do that. But then a lot of organizations are increasingly moving some of their ingestion pipeline to more of a near real-time type of approach. So there's data sources that doesn't come at you in batch, it actually comes at you in near real-time. And your ability to deal with that is really key, because if you can respond to those events in near real time, then that potentially gives you an enormous advantage in the marketplace in interacting with your customers or dealing with events as they come up. Now, then we move into the serving layer. So the serving layer is really the key area where you then allow your consumers, your users, or potentially other downstream systems to then actually start to analyze and make sense of this data. And so we'll talk through that serving layer as well. And then in terms of the actual constituents, now obviously there's a huge number of different roles and different people that are interested in doing analytics on this data, but the key roles that we see are obviously the data scientists, who are very interested to run all sorts of interesting algorithms across the data sets that you have. You then have the data analysts, who are often using things like SQL and other languages to interrogate the data. There's obviously business users as well, who are typically using some kind of business intelligence tool to get analysis done. And then you have other systems as well. So you might have an engagement platform. So this really relates to how do you then engage with your customers, whether it's to make them a recommendation or potentially a next best offer, etc. That all might come out of the analytics that you do within your architecture. And so the ability to then do that analysis and then take action on that is absolutely key. And then obviously in that vein, you've also got automation and events as well. So it might be that based on something that you see within the architecture, some analysis that you've done, you then actually want to automate some kind of downstream step or take advantage of some kind of event. So we're going to talk as we go through this architecture. Now, obviously, I'm going to talk a lot about the Amazon services in this space, but I don't want you to think that it's an all or nothing approach to each of these, that it must be an Amazon service. One of the things that we see is we see a lot of environments where some of the services are Amazon managed services. Some of them are obviously our partner tools or open source products as well. So I am going to focus on the Amazon stuff, but I want you to keep in mind that each of these components, it's very much a mix and match type of approach, where if that particular service doesn't quite work for you, then you can certainly spin up a virtual instance and install on there whatever you like. Now, wrapped around this are some other really key elements as well. So obviously security, we talk about being job zero for us, to make sure that that's the first thing we always think about whenever we introduce a service. And we encourage customers to think that way as well. So we have something called AWS IAM, which is our identity and access management service. So this allows you to control who can do what within the environment. There's also KMS. So KMS is the key management service that allows you to manage the encryption keys for any encryption that you do, and that obviously then makes it easy to encrypt and decrypt, so that you can keep the data encrypted, but then those services can use them as they need to. AWS CloudTrail can then log all the API calls to each of your services as well, so you can keep track of that. And then CloudWatch as well will then give you more of a metrics view over what's going on in your environment. So again, just talking to the manageability aspect of the data architecture, to have a lot of that plumbing already in place for you just makes the management of the whole thing much easier. So that's the framework we're going to talk through, and we're going to look at 4 of the main patterns that we come across when we talk to customers. So the first is database analytics, and the use case here is typically that every organization's got databases spread throughout the enterprise and the organization, and the use case is that typically people are running out of oomph in that particular database. They're running analytics, but the queries are slow, or they can't get access to all the history that they'd like to, or the data is aggregated, it's summarized for performance reasons, so they want to get down to the atomic data. So we'll look at that use case. So how do you deal with that? How do you give your users access to more data faster? Then we'll look at flat file processing or batch processing, and this is obviously a key component of many architectures, and these files might come from internal systems, or often they come from external feeds. How do you get them in there, and how do you actually then process them? And then we'll move on and look at the real-time pipeline, or as my colleagues like to tell me, that it's not real-time, it's near real-time. So we'll talk about a near real-time pipeline. And then we'll kind of bring it all together and have a little bit of a chat towards the end around the data lake. What does the data lake look like? So let's start off with database analytics. Now, this is probably one of the most common use cases, or often it's the first use case for many customers, because often it's the most burning issue that they have, because they do have a lot of databases that are often running out of steam. So the sources you'd expect is some kind of database. Typically it's a traditional row-based database, and it might be running out of steam because maybe it wasn't really designed for analytics in the first place, but it's now being asked to do that. Or maybe it's simply that it's being overloaded with the amount of data that's being put in there and the types of queries that people are asking. So one of the common patterns that we see is customers using a service like Amazon Redshift to deal with this issue. So let's have a little bit of a dive into Redshift. So Redshift is an MPP SQL database. So MPP stands for Massively Parallel Processing, and it's a breed of databases that have been around for a few years, and essentially they take a very different approach to running queries against the data, in that they spread the data very widely across a large number of nodes within a cluster, and that means that they are absolutely optimized for analytical queries. So typically an analytical workload is one where you scan a lot of data, and so if you've got that data spread across a lot of machines, then obviously you can churn through it much more quickly. Now, back to the scalability type aspect, you can scale this from a couple of 100 gigabytes through to the petabyte range if you need to, so you know that you've got that headroom there to grow as you need to. And it is fully relational, so sometimes there's a little bit of confusion around some of these new breeds of databases like MPP and column databases, etc., that they're not fully relational. MPP databases like Redshift are fully relational, so you create tables as you would normally. You can typically use the same data model that you use in your existing database. You create the tables, you create joins between tables, etc. So often very easy to migrate because you essentially pick up the data model that you have and move it across. So just looking under the hood into Redshift a little bit. So this is the typical architecture where you have a leader node at the front, and this is the node that your tools or your SQL clients will talk to. And then you've got the compute nodes where the data lives and where all of the compute power is. And this is the layer, the compute layer, that you scale out horizontally as you need to. So typically you have a number of tables, and what you do is you then, when you load those tables into Redshift, they get spread across all of the nodes in the cluster. So each of those nodes has access to its slice of that table, and we call this a shared nothing architecture because the nodes are extremely selfish, which normally we try and discourage, but in this particular instance it's actually a very positive thing, because then they can, there's no contention issues as you scale out that layer. Those nodes are self-contained, so they've got their own CPU, their own memory, and their own disk, and they're able to just run their queries independently of other nodes. Now, obviously, occasionally there's need to share data, and they can obviously then do that. But again, we do that at a parallel level so that you can maximize your performance. So what happens is a query comes in from the tool. That SQL then gets pushed out to every single node. So the same query goes to every node, and each of those nodes runs that query against its data slice, gets the intermediate result sets back, and then pushes the results back to the host. There's lots of other smarts in there as well to try and speed up your queries, but that's one of the main reasons that databases like Redshift do scale, is because of that ability to spread the data very widely. In terms of scalability, so I talked about it going from gigabytes to petabytes, so you can start off with a single node if you wanted to just dip your toe in the water and have a bit of a feel for how it works. So that's 160 gig of disk, but then, as I said, you can then grow that cluster up into the 2 petabyte range if you need to. So that's all good. We've got Redshift there. The big question now is, how do we get data from the source database into Redshift? So the ETL market has been around for a very long time. So ETL stands for extract, transform, and load. And this is a very mature market with a lot of excellent tools out there, many of which are fantastic partners of ours to help you to get data out of those source systems and into Redshift. And basically they will interrogate that source database and just push those changes straight across. So just delving into that a little bit more, so we've got, as I said, many partners in this space. So if you actually, into your favorite search engine, if you put in Redshift data integration partners, that'll lead you to the page on the website, and it lists all of the tools that work well with Redshift. We also have our own tool called the AWS Database Migration Service as well. And what a lot of these tools do is to reduce the burden on that source database, because often that source database does still have a day job, it still potentially is supporting an application, is that they'll actually look at the transaction log of that source database. And in reading the log, they'll pick up all the changes that have happened to the tables that you're interested in without actually having to run a query against the database itself. So designed to be quite a lightweight process. They pull the changes out and then they push those across to the target, in this case Amazon Redshift. Now there's another slight variation on this which is called ELT. So ELT is where you extract from the source, then you load it into your target database, and then you do the transformation. So that looks a bit like this. So you would extract from source, load it into Redshift, do the transformation in database, and then move that to another table. So even though I'm showing this as two different clusters, this typically happens within the same cluster, within the same database, and you're just moving data from one table to another table. But the advantage of doing the ELT approach is that you're taking advantage of the power of the Redshift cluster. So as I said before, it's got a lot of processing power in there, and especially for customers who are bumping up against that batch window issue. So often I talk to customers who are having issues where they're essentially running out at night time because the amount of data that they're having to process overnight is getting bigger and bigger, and they have an SLA where they want to allow their users to start accessing the data as soon as they come in the morning, but that batch process is taking longer and longer. So often we see that an ELT approach can help with that, because then you're using the power of the database. It's got a massive number of CPUs potentially in there to help you to crunch through that much more quickly. ELT doesn't work for every type of transformation, but it's definitely worth taking a look at. So somebody who's done this very effectively is Boingo Wireless, and they obviously collect a lot of data. They moved from a traditional row-based database across to Redshift, and they found that they had queries that were taking 45 minutes on their existing system that were now running in 20-25 seconds on Redshift, and they found that their loads, which used to take a couple of hours, were now taking tens of seconds. So they had a 1 million row load that took about 25 seconds to load up into Redshift. So that's the type of performance gain that you can see when you move to a database that's dedicated for that particular process. If you're interested in that use case, have a look for Boingo and Redshift, and it'll take you to the case study. And they also did a presentation on that at reInvent a couple of years ago, which is excellent too. So let's have a look at flat file processing, and this is more of the batch approach. So let's say we have some flat files that have come from somewhere, either internally or externally. One of the fantastic places to put that flat file is into Amazon S3. So S3, if you're not familiar, is the simple storage service, and it's an object store that is extremely low cost. So if you look at the cost of it per gigabyte per month, it's extremely low. It's very, very scalable. So again, back to the scalability question, you don't need to pre-provision Amazon S3. You simply load data into it as you need it. And it's got 11 nines of durability, which means that every object that you give to us that you want to put into S3 will actually write that to multiple physical locations within a region. So if you take the Sydney region, for example, that's got multiple separate facilities within that region, and we'll write that object to multiple places to ensure that we can give you that level of durability. So the great thing about that is that then if you're using that as your basis to store data, you don't need to then back it up again, because basically we've taken that heavy lifting off your plate for you. So how do you get data into S3? So there's lots and lots of ways. Just a couple I wanted to mention. So you can use open source log aggregation or collecting type software like FluentD, for example, Log4j, which is a logging application. We've also obviously got a command line interface and our own SDK, but there are many other options as well, including if you find that you've got a lot of data that you need to move, especially historical data, you can also use the AWS Snowball. So this is the appliance that we actually ship to you. You load your data onto it, ship it back to us, and then we'll actually load that into S3 for you. So you can move an enormous amount of data very quickly using that kind of approach. So let's say we do that. We've got data in S3, and now we want to do some kind of transformation on it. So this is where we see technology like Hadoop really coming into its own. And I thought it might be worth just giving you a quick potted history of Hadoop, because that history, I think, then really kind of talks to some of the stuff we want to mention later on. So if you look at how we did things in the good old days before Hadoop, it's almost difficult to imagine a world without Hadoop, but there was a time where we didn't have the elephant in our lives. And if we wanted to do processing on data, we would load it up onto a machine, and then that machine would have a certain amount of compute power, and then obviously we would churn through our job. And if we wanted to make it go faster, we would then get a bigger machine with more compute power, which would allow us to either go faster or load more data up. But as Grace Hopper famously said, in the pioneer days they used oxen for heavy pulling. When one ox couldn't budge a log, they didn't try to grow a bigger ox. Now, she was ahead of her time here. She talked about this in the 1960s, but she was referring directly to using clusters of machines to distribute the load. And if you're not familiar with Grace Hopper, look her up online. She's really, really interesting, and obviously had quite a heavy influence on IT. So what she was suggesting, and obviously what then happened, was that if you could distribute your processing across a large number of machines, then suddenly you can go much wider with your processing. The problem, though, is that you need something that's going to manage that, because you need to know where bits of data are, because they could potentially be on different machines. You need something to coordinate the processing between each of the machines. And so this is really where Hadoop came into its own as a framework for managing these kind of large distributed clusters. So if you look at the Hadoop stack, so you start off with some kind of infrastructure. Now, if this is on-premise, obviously there's going to be physical machines. In the cloud, there will be virtual machines. HDFS is the data layer, so this is Hadoop's distributed file system, so this keeps track of where all the bits of data are in the cluster. MapReduce was the original process layer that was designed to work across HDFS. Hadoop was the framework, and this kind of served us well for a small amount of time, but IT professionals, being the impatient bunch that they are, said, well, we can make this better. We're finding MapReduce is a little bit clunky and hard to work with. We'd prefer a kind of a higher level language, and so applications like Hive and Pig were born. So Hive was, and still is, a SQL-like language that then will translate your kind of SQL commands into MapReduce for you, so you're not having to deal down at the MapReduce level. And similarly, Pig's got its own higher level language for manipulation. And that was great for a while, and then somebody said, look, MapReduce is getting a little bit slow and clunky. We'd like to speed that up. And so we saw a couple of new entrants into the process layer, namely Tez and Spark, and these guys are really have really taken over from MapReduce now. MapReduce is really kind of considered to be kind of the old world, if you like. And along with that, then sprung up a massive number of applications as well. So we saw things like Presto, for example, again designed to give very fast SQL access to data, HBase for NoSQL applications, and then Spark itself comes with a number of different modules. So there's a SQL module, there's a streaming module, etc. There's an R module, graph database, etc. Really kind of filling out that ecosystem within the Hadoop framework. So that's all well and good, and so obviously you can do this within Amazon. Those machines at the bottom, you can spin them up as EC2 machines. You can install your Hadoop distribution of choice and then install your applications on top. But we saw a lot of customers doing this, and we thought, wouldn't it be nice if there was a managed service that took away some of that heavy lifting? So we introduced Amazon EMR, and this is a managed Hadoop service. So what this does is it provisions the machines for you. It will then install Hadoop. It'll make sure all the nodes are talking to each other. It'll install the applications that you want, so that you don't have to do that. You can basically just focus on actually using the applications and doing something interesting with them. Now, EMR introduces another really important element, which is something called EMRFS. And what this does is this allows you to use S3 as your data layer. And this has a couple of really important benefits. The primary one being that you can now decouple your storage layer from your compute layer with your Hadoop clusters. So what that means is that you can just load data into S3 as you need to without necessarily having to scale up your Hadoop clusters. You can then bring up the Hadoop clusters that are much more closely matched to the type of processing that you want to do. So let me give you an example of that. So within the EC2 family of virtual machines, we have a number of different families that have different characteristics depending on what you want to do with them. So there's general purpose, there's ones that are more compute heavy, ones that have got more memory, etc. And if you look at the types of big data analysis that people typically do, they can lend themselves to a very specific configuration. So batch processors obviously aren't too fussy, but things like machine learning really loves CPU, and so if you can have a much more CPU intense type of instance, that's going to obviously assist that machine learning workload. Similarly, with a lot of the interactive analysis, Spark and Presto, etc., they love memory. If you can provide instance with more memory, it's obviously going to be a lot more efficient. So that ability of EMR to allow you to then spin up clusters separate to the storage layer allows you to bring up clusters that are much more closely matched to the type of workload. The other really interesting thing that you can now do if you've decoupled your compute from your storage is you can take advantage of this relationship between cost and time in the cloud. So the way that you pay for your compute in the cloud is essentially the number of CPUs that you are using and the time that you're using them. So let's say you have a job that you throw one CPU at it and it takes 10 hours to run. You're going to pay for that one CPU for 10 hours. But let's say that that particular job is one that lends itself to be distributed across a number of CPUs. If you then throw 10 CPUs at it, it then might take an hour. But the key thing is you're still paying for exactly the same amount, because now you're paying for 10 times the number of CPUs, but you're only paying for them for a tenth of the time. So the cost is exactly the same, but the impact to you is that you're now obviously finishing your job much, much sooner. And so this is one of the key aspects of the modern data architecture, is this scalability and the ability to scale very widely but for a short period of time. So you go wide, you do what you need to do, and then you either scale back in or you shut that cluster down completely, which is very difficult to do. Obviously, if you have to buy those machines, then obviously you're not going to scale them out as widely as you potentially could. Now, the other aspect to this as well around cost is that you can also then take advantage of the spot market. So the spot market is any unused EC2 capacity that we have for a given instance type will make available to the spot market for customers to then bid on how much they'll pay for it. Now the spot price is obviously, it's a fluid kind of price because it's a fluid market depending on supply and demand, but typically the spot price is a fraction of the on-demand price. So to give you an example of that, if you look at the M3 2 Extra Large, which is a fairly kind of middle of the road instance type, in the Sydney region, the on-demand price for that is 75 cents. So the on-demand price is where you say, I'm going to use this instance, and basically you can then use it for as long as you want, and then when you're finished with it, you can stop paying for it. That'll cost you 75 cents an hour. The spot price, as I said, it does fluctuate, but it's often around the 8 cents an hour mark. So you can see that's a significant difference, and that then potentially allows you to spin up a very, very large cluster and get your processing done even more quickly, but obviously save a lot of money on that. Now I can hear you asking, well, that sounds fantastic. Why don't I run everything on spot? Why would I ever pay the on-demand price? Well, the caveat here is that if the spot price goes up and it goes above what your maximum bid was, then we may take that instance away from you. So you really need to use it for workloads that can tolerate the loss of a node, and we've baked that functionality into EMR to allow you to very easily take advantage of the spot market, spin up very, very big clusters, but not be impacted if one or two of those nodes then gets taken away from you. So going back to our framework, so in our scale out box here, we've got data landing in S3, EMR or Hadoop doing some transformation, putting the data back in S3. I also just wanted to quickly give you a glimpse into a service that we've got coming out later this year, which is AWS Glue. So again, and you've heard me say this a couple of times, that we saw customers running very, very similar types of workloads. We saw this across customers, across industries, etc. And that was using Hadoop and EMR to do transformation. So when we see that, often we look at that as an opportunity to maybe introduce a managed service to take some of that heavy lifting off you. So Glue is designed to be that kind of transformation as a service piece. So it's going to be a managed transform engine. It's going to have a job scheduler built in, and also a data catalog, so you can see where data's come from and where it's going. And it's built on Apache Spark. So just a quick screenshot so you can see basically that you're managing your jobs there, and you can see how many rows have been read, written, errors, duration, etc. So you can keep track of the transformations that are running in that environment. So that's currently in preview, so if you're interested in having a bit of a look at that, sign up for the preview. If you just look for AWS Glue preview in your search engine, it'll take you there. And that preview is currently in the US, but you can get your hands on that to have a bit of a play with it. So we've done our transformation in that layer. Now in the serving layer, how are we going to get this data to our consumers? So we could load the data from S3 into Redshift, and that's quite common. We could also then use a different EMR cluster or Hadoop cluster to also access S3. So if you look back to our stack, a lot of the applications that fit into Hadoop are really designed for interrogation and analysis of data. So Spark R, for example, allows you to run R against that data, Spark SQL, Hive, etc. And if you look at that one on the top left, Presto came out of Facebook, and it was really designed to sidestep a lot of the inherent inefficiencies in the framework to really give users very fast SQL access to data in HDFS and also in S3. So we saw this became a common pattern with customers that were spinning up clusters to use Presto to then access their S3 data. And so again, we thought, well, maybe that lends itself to a managed service. So that's what we did. So we introduced Amazon Athena, which is built on Presto, so it's Presto underneath, and it gives you that SQL access to your S3 data. Now, it is serverless, so basically you don't have to actually provision or spin anything up. You simply just run the query, and we will then provide you the cluster that will then access the data and give you the result set back. And you then pay that per query, not per hour or anything like that. So very simply how it works is you've got data in S3 and you have users who want to run SQL queries across that data. At the time that they run the query, we'll then move that cluster into your account. You can run that query. It will then interrogate S3, bring the result set back, give that back to the users, and then that cluster will disappear. So as I said, it's not you don't have to worry about any infrastructure. You're basically just running queries against your S3 data. So we've introduced a couple of different options for running SQL queries, and so the question that often comes up is, well, how are these all different, and when should I use the different types of SQL engines? So I just thought it might be worth just giving you a quick comparison of these. So if you look at Hive and Spark SQL on the left there, we'll compare that with Presto, Athena, and Redshift. So if you look at the data structure that they support, the first three can deal with highly structured data or semi-structured data, whereas Amazon Redshift is a database, so really requires that data to be fully structured. The languages it supports, so the last three, Presto, Athena, and Redshift, support ANSI standard SQL, as does Spark SQL, and then Hive gives you that kind of SQL-like language. And the data stores that they can access, so Hive and Spark SQL can talk to S3, HDFS, actually, and other data stores as well. Presto, similarly, primarily S3 and HDFS, but also has connectors for other databases. Athena is S3 only, and Redshift talks to its own local store. So in order for Redshift to query data, you actually load it in to Redshift, as opposed to the other three, where you're actually just pointing the engine at data that lives somewhere else. And then in terms of performance, this is kind of the gradient we're talking about. So Hive and Spark SQL, they're not the fastest SQL engines out there because they're a bit more general purpose, they're sitting on a more general purpose framework, whereas Presto is designed specifically for SQL, so it's a lot faster. And then Athena has a very similar performance footprint to Presto because it's essentially Presto underneath the covers. But then you'll find Redshift is going to be the fastest, mainly because that data is local, so it's local to the processing nodes, but also it's a dedicated database engine specifically for fast SQL queries. So what kind of use case then do these facets lend itself to? So we find that Hive and Spark SQL tend to be used more for transformation type of workloads, as opposed to queries where you're kind of expecting a result set back. It's more for transforming data from one format to another, for example, or you're actually putting some business logic into that transformation as well. And then Presto for SQL queries that are going to hit S3 or HDFS. Athena is similar, but you want a more serverless approach where you just want to run the queries without having to worry about a server. And then Redshift is much more a fully featured SQL database. So think about more of a data warehouse or a data analytics data mart, for example, where you need some of the facets that a database will give you. Now, it's not all or nothing as well. We have a lot of customers that use a combination of these. So one quite common pattern is to use Redshift for very hot data, for example, where you've got people that are running queries, are expecting a very quick result. That might be, let's say, the last 2 months worth of data. And then the older stuff still needs to be able to be queried, but maybe not quite as quickly. So often customers will put that data into S3 and then have a Presto cluster or Athena sitting on top of that, so that their users still get SQL access, but don't need it quite as quickly. Now, one of the best examples I've seen of a customer who has successfully decoupled their compute from their storage is FINRA. So this is the Financial Industry Regulatory Authority in the US. Now, they're tasked with looking at a lot of the trade data that goes through the financial market, specifically looking for things like fraud, etc. So often they'll look at upwards of 75 billion records a day, and So for them, this ability to scale up and down is absolutely crucial, because if they have a particularly big trading day, then obviously they're going to have more data that they need to crunch through. And if they have a lighter trading day, then they don't need as much compute power. And sometimes they only need that compute power for a very short time. So they're a great example of a customer who uses that scalability. They also take advantage of spinning up very dedicated EMR clusters for specific purposes. So they have batch clusters, they have query clusters, etc., etc. So a great example of decoupling that storage from compute. So let's move on to our real-time pipeline. So the types of data that are characterized in the real-time pipeline are, for example, things like data that's been generated from machines. So you might be getting telemetry from machines around the state that they're in, etc. But obviously devices are becoming very popular as well. So you might have devices that are sending data back every few seconds about their state. Mobile is another big driver of the real-time pipeline. So you have data coming off the mobiles. It might be location data, or it might be in-game data. So we have a lot of customers who create games, and they actually want to get a lot of telemetry from within the game to see, you know, how players are going. Do they need help? Are they getting stuck? That kind of thing. And then obviously clickstream data as well is very popular. So instead of getting a weblog every hour or at the end of every day that contains everyone's clicks, you actually set it up so that you get them in near real time. So as soon as someone clicks on a link, you get that event straight away. And that obviously gives you the ability to then do something about that in near real time. So if you're going to ingest this type of data, you need something that can cope with potentially a lot of throughput, but it needs to be able to store these messages durably. So we have a service called Amazon Kinesis. And if you look at Kinesis in a little bit more detail, so you've got your data sources there. Kinesis, similar to S3, it sits across 3 availability zones. So availability zones are our separate data centers. And so every message that you send into Kinesis, again, will write that to multiple locations to make sure that we store that durably. So you create a stream within the Kinesis service, and then that gives you an endpoint, and then those sources can then push the messages into that endpoint. Now the idea with the stream is that you then want to have multiple applications at the back end reading from the stream. And so you don't want messages to be hidden from each of these applications. You want the same message to be read multiple times. So messages will stay in the stream until they age out. So the default age in the stream is 24 hours, but you can push that to 7 days if you need a bit of extra time. Now there's a few different ways to get data out of Kinesis. So you can, for example, write your own application. So the KCL is the Kinesis client library. So this is a bunch of libraries that help you to write your application against Kinesis. And so that would run on EC2 machines. And then that would obviously pull messages off and do whatever you need to do with it. A lot of customers, though, are moving much more towards a serverless approach. So they prefer to use AWS Lambda for this. So Lambda is essentially a serverless framework where you just give us your code, and then we will then run that code either in response to an event, or in this case, it will actually, your code will sit there and Lambda will poll Kinesis waiting for messages, and then when those messages come off, it will then fire off your logic to then do whatever you need to do with the data. Another popular option is actually, again, to use Hadoop or EMR in conjunction with Spark Streaming. So Spark Streaming is designed specifically for allowing you to process streaming data by creating micro batches and then doing something with that data. So three common approaches. Now, what we then see customers doing with those types of things often fall into some very broad categories. So the first thing often that people will do is they'll just create a log of every message that comes through. They just want to know that they've got that sitting somewhere. They also want to create real-time dashboards so they can actually kind of see what's happening at any given time. They might want to do deeper analytics on it. Another common use case is actually to do predictions on the data. So based on the data that's coming through, use some kind of predictive algorithm to try and predict whether maybe if we're getting device data, is this device about to fail based on the telemetry data we're getting back from it. And also then we might just fire off an alert. So if we see that a particular message is out of bounds, for example, we might actually then trigger off an alert system which lets someone know. So how does this map back to our framework? So you can see there we've got Kinesis in the ingest, and then in our real-time pipeline we've got our 3 different options for dealing with the data. And then for our logging application, obviously an obvious choice for that is to put that into S3. For real-time dashboards, one of the most common places for that is Elasticsearch. So if you're not familiar with Elasticsearch, it's an open source real-time search engine and also analytics platform that's been around for a while, but very, very popular, very scalable. And we found a lot of customers were saying, look, we really love Elasticsearch, but we really don't want to manage the cluster anymore. Can you come out with a managed service? So we did that. So that's what Amazon Elasticsearch is. It's essentially a managed Elasticsearch cluster, integrated with the open source ingestion and also the visualization tools such as Logstash and Kibana. So if you're not familiar with Kibana, it's a great way to create real-time dashboards, very easy to use, and used a lot for this type of thing where you just want to kind of get a quick snapshot of what's going on in your environment. For the analytics use case, obviously Redshift is an obvious choice for that. For predictions, we might see again Hadoop or EMR being used with something like Spark machine learning. You might be sick of seeing the Spark logo come up. It seems to pop up everywhere. But this is the beauty of Spark, is that it's got so many different modules to it that it really is an extremely flexible processing engine. And then you might use SNS, which is the simple notification service, to send off alerts. So if you pick something up in your real-time pipeline that wasn't quite right, you can then obviously send off an alert for that. Now, I just wanted to mention Airbnb here. They've just recently open sourced something called StreamAlert, and they've built a framework on top of a lot of the services that we've talked about here, Kinesis and Athena, Lambda, etc. And they've open sourced that. Really, really interesting. So if you're keen to have a bit of a read through that, just do a search on Airbnb StreamAlert and have a bit of a read through. They blogged about it a couple of days ago, and really nice use of the technology. So just moving to our last use case. So if you think about the concept of a data lake, now not everyone likes the term data lake, but essentially when you look at the data lake or the data hub or whatever you prefer to call it, the main facets of it, when you look at all the definitions and you distill out what it's really talking about, there's really two sides to this. The first is that you can put any data in the data lake. It's not just about structured data. It's about pretty much anything you have. Any data can go into the lake. And then at the other end, it's about any analysis. And so you're allowing users to use the tools that they want to access the data. You're not saying to them you can only use SQL. They can use whatever they like. So that for me is really the essence of the data lake, is any type of data and any type of analysis. And so when we map that back to our kind of architecture here, all this really is essentially just all the 3 things that we've talked about. So it's all the different types of sources, so it's databases and flat files and real-time sources. It's the different ingestion mechanisms depending on what the data source is, and then it's either pushing that through your batch layer, but also taking in your real-time feeds and then also pushing them into to be married with the batch data as well as doing things with them in near real time. So we often see this use case where the whole point of having the speed layer is that you can see that data very quickly, you can see it in real time, and you can react in real time, but you also then want to have that data available for later analysis as well, and be able to then marry that back to the other data sources that are coming through. So that's very common, is to see your speed data going in two different directions there. And then the serving layer, obviously we've just I've put a few down here, but we see Redshift for analytics, EMR for the host of different Hadoop applications, Athena potentially for that SQL access, and then EC2 as well. So obviously on EC2 you can run up any application that you like, and that gives you tremendous flexibility. And then those consumers, those constituents on the far right hand side there, can then access that data in whatever form they want to. They're not going to be constrained by a particular tool. And then of course the other kind of wrappers around this that we talked about as well are going to play into the data lake as well, making sure you've got the right controls in place, the right encryption levels, the right audit trails and monitoring, etc. So that's essentially what I wanted to take you through from an architecture perspective. I just wanted to make a quick mention of the X1. So we talked about the different instance types that we have, and obviously one of the things that comes up a lot is how much memory some of these instances have. So the X1 is relatively new. It's really designed for in-memory applications at a very large scale. So if you look at some of the applications that are good for it, so we've talked a lot today about Apache Spark. We've also talked about Presto as well, but also SAP HANA as well. We see that as a target for the X1 too, where you need that big memory footprint. And HANA is a great example of that kind of serving layer where you're able to give your users very fast response time. It's got the Intel Haswell processors in there, so lots of great grunt there, up to 2 terabytes of memory, which is nice, and up to 128 vCPUs per instance. So quite a lot of power in these instances, and for the right use case, can be extremely useful. Now, while we're on the subject of Intel, because as I said, we were in partnership with Intel for this webinar, there's actually a lot of Intel smarts in a lot of the instance types that we have, and so they've done a huge amount of work around obviously putting, as I said, more smarts into the processing. And if you jump onto the AWS website, there's an Intel page there that's really interesting. It talks a lot about these technologies, but also talks about the different instance types that we have and which of them support some of these different technologies. So if that's of interest, jump onto the AWS page and have a look at that. And then just finally, before I go, I just wanted to also mention that while listening to me talk is obviously extremely exciting, getting hands-on is really where you start to get a feel for the technology and start to understand how it all fits together. So what we've done is we've made some self-paced labs available for you to use, and so if you can register by jumping onto that URL, and they're going to be free until the 31st of March this year. So if you want to jump on and get some hands-on, then feel free to do that. So I shall leave that there, so you can follow that link if you need to, and I shall sign off. So thank you very much for your time today. Thanks very much for joining, and best of luck in creating your modern data architecture.